Cut power to a traction elevator, and its first brake does not release. It closes, but that is only layer 1. If the car still accelerates, a second system measures speed without trusting the main motor and turns the guide rails into brakes. A blackout and a descending overspeed are different failure paths, so they need different answers. The reassuring answer is not one unbreakable cable or one perfect computer. It is a stack of different mechanisms. Suspension carries the car. The machine brake holds it. A governor watches speed. Car-mounted safeties grip the rails. Buffers wait at the bottom for travel beyond the normal limit. No single layer is asked to solve every possible fault. Start with the ordinary ride. In a traction elevator, the motor turns a grooved sheave. Suspension ropes or belts pass over it, with the car on one side and a counterweight on the other. Rotate the sheave one way and the car rises while the counterweight descends. Reverse it and their directions swap. Traction at the sheave transmits motion without winding the suspension members onto a drum. The counterweight does not exactly match every passenger. It balances the car and a chosen share of its rated load. That means the machine mostly overcomes the difference between the two sides, plus friction and acceleration, instead of repeatedly lifting the full mass of the car from scratch. Balancing part of the load also reduces the energy the drive must supply over repeated trips. Now look above the car. Modern traction elevators use multiple suspension members, not a single movie-style rope. Their materials, terminations, design margins, inspections, and replacement rules are treated together as a safety-critical system. ASME's suspension standard covers steel wire ropes, coated suspension members, design, testing, inspection, and replacement. The animation shows the principle, not the exact member count of every installation. At the machine is a friction brake. Its job is to prevent motion when the elevator is stopped. The clever detail is the direction of failure. Springs push the brake shoes onto a drum, disc, or pulley. Electrical force is used to lift those shoes away while the car is commanded to move. At rest, spring pressure exists without a fresh command from the controller, so a blackout removes the force that holds the brake open. The springs close it. The car may stop between floors and require a controlled rescue or backup system, but loss of ordinary electrical power is not permission for the machine brake to let go. A backup device may move the car later. The brake's fail-safe direction comes first. That brake is powerful, but the safety case cannot end there. A control fault, a mechanical problem, or loss of traction can create a descending overspeed condition. The next layer needs its own view of car speed and a mechanical path that does not depend on software making the right decision. Independent speed sensing can catch motion that a position command failed to predict. That watcher is the overspeed governor. A separate governor rope forms a loop through the shaft and is attached to the moving car. As the car travels, the rope turns a governor sheave at a matching speed. It is not one of the suspension members carrying the passenger load, it is a mechanical speed signal. Because the loop follows the car continuously, its rotation directly represents car motion. Inside a common centrifugal governor, rotating weights want to move outward. At normal speed, springs and geometry keep them inside their operating range. The wheel can spin all day without touching the emergency mechanism because speed, not mere motion, is the trigger. It monitors every ordinary trip while remaining mechanically ready for the abnormal one. As speed rises, the weights move farther outward. At a preset overspeed, the governor opens the safety circuit so power is removed and the machine brake is applied. If the car still accelerates to the mechanical trip point, the governor moves from warning the system to physically gripping its rope. The electrical intervention therefore precedes the final mechanical rope grip action in this sequence. This distinction matters. The governor does not reach down and clamp the passenger car. Its jaws seize the governor rope. Now the rope is stationary while the car and its frame still have downward motion. That difference in motion supplies the pull for the next mechanism. Stopping the rope is useful precisely because the car-mounted linkage remains in motion beside it. Imagine holding a strap still while its mounting frame slides downward beside it. Relative motion appears between them. On the elevator, the stopped governor rope pulls an operating lever on the moving car frame. That lever converts a small rope displacement into a decisive movement of the safety linkage beneath the car. It is a mechanical comparison between two motions, not a software estimate of what should be happening. A cross-linkage applies safeties on both sides of the car frame. The goal is symmetrical engagement with the two guide rails, not a single hook catching the cabin. The same rails that guide the car smoothly during every normal trip now become the surfaces that can stop it. The safeties act on the structural car frame that carries the cabin and its load. Here is the geometry that makes the mechanism so elegant. A wedge is drawn into the narrowing space between the car frame and a steel guide rail. Continued downward motion drives the wedge tighter, increasing the normal force and therefore the available friction. The failure motion itself helps build the stopping force. Geometry, surface condition, and allowed travel must be engineered so that force grows in a controlled way. For faster cars, the safeties are designed around controlled stopping behavior. The jaws or wedges develop friction over a finite travel, bringing the car to rest and holding it on the rails. This is not a cartoon, Paul, slamming into one tooth. Safety codes specify stopping distance limits for defined safety types, loads, speeds, and test conditions, so exact values belong to the certified installation. That gives the guide rail two very different jobs. Most of the time, it keeps the car aligned and the ride smooth. During a descending overspeed, the car safeties turn it into a structural braking surface capable of stopping and holding the frame. The rail system must therefore support emergency forces as well as routine guidance. At the bottom of the hoistway are buffers. They are designed for a car or counterweight that travels beyond its normal lower limit, storing or dissipating kinetic energy. Oil and elastomeric buffer designs have construction and type testing requirements for their intended service. They are an additional final layer, not an excuse to let a full-speed free-fall smash into a giant spring. Now the design philosophy is visible. Carry the car with multiple suspension members. Make the service brake fail toward closed. Watch speed with a separate mechanical governor. Let relative motion engage rail safeties. Keep buffers for travel beyond the normal limit. Each layer addresses a different route to danger. This is layered defense, not 5 copies of the same sensor making the same assumption. So the hidden trick is not that elevators trust one component completely. The system is arranged so several failures create a stop command or a mechanical brake action. Power disappears, the first brake closes. Speed keeps rising, the governor and rail safeties take over. The transferable lesson is fail-safe direction. When energy or confidence disappears, move toward a safer state. That is engineering by layered consequences.